much, Casey. So this talk is a little bit more higher level, a bit more abstract than the talks we've seen, but I don't think I could have asked for two better talks to follow in terms of what I'm about to talk about. So a lot of the work that I've been doing at Cambridge has been related to tools for scientific programming, but I didn't stop for a long time and ask myself, well, what even is scientific programming? And I think trying to come up with a succinct definition is quite hard. And particularly, I think we might run into difficulties here with the scaling, but we'll see. We can run into difficulties whenever we try and come up with some kind of exhaustive list of what scientific programming is, where we might try and enumerate all the different things that might constitute scientific programming, whether it's climate modeling, data science, geospatial analysis, all these things. They seem to fit the bill, but they're all quite different. And I originally started from a place of wanting to say, what do they have in common, and maybe how do they differ from what we might consider conventional programming, something like building a high-performance web server or something like that. And I think there's definitely merit to doing that sometimes, but I think you'd be able to find some version of scientific programming that actually is very close to doing high-performance web server work. So instead, I think an interesting way to look at this is to focus in on what makes it scientific to begin with, instead of the programming aspect. And so thinking about that, I think leads to trying to think about the scientific method itself. And there's been some work by a few different people on trying to link the scientific method into scientific programming and come up with actually these properties that are inherent to the scientific method, and then ask ourselves, does our scientific programming adhere to these properties? And that's both in terms of the data and the code. And so often things that come up are things like falsifiable hypotheses, repeatable experimentation, and also reproducible methodologies. And so the distinction between those last two things, which I find hard to understand, I think, is that the repeatability is kind of, given the exact same experimental setup, can we get the same results? And the reproducibility is more, given just the information on how someone did something, can we go away, build our own version, and get the same results? And those two things are kind of equally important and obviously quite interlinked, and can be interchanged in some scenarios. So I think a useful set of axes to think about, these different ways that we might adhere to these properties, is in the data, the code, and in the programmers. And I wanted to talk about the data first. And so this has gone slightly off screen, but hopefully there's enough on there to be able to see what's happening here. I realized that I gave a talk last time at PROPL in 2024 where I showed the same slide. And late last night, I realized I had not adhered to my own kind of want to keep things updated as new data comes out. And I had the 2022 data set. And so late last night, I wanted to update this to 2024. And to give more details on how I actually went about that, it wasn't easy because I didn't have the code lying around. And I realized I didn't have my SSH keys on this laptop. And so there was, for me, a late night phone call to my partner asking them to send over an encrypted message channel, my SSH keys from my MacBook that's back in Belfast. So I could log into a server that's in Cambridge, so I could find the script that I could put into Google Earth Engine and rerun the results for 2024. So I think there's a lot of work to be done. I think even someone who's been in computer science for 8 years is still making these kinds of mistakes is probably, hopefully not just my fault, and hopefully more symptomatic of the tools that we have. Unfortunately, the actual results from this are not good at all. The previous slide is exactly the same year, so it's 2008, it's Indonesia, and we're looking at the different land classifications for forests. And so the main thing to see is that orange is deforestation. So for exactly the same year, but just an updated version of the data set, there's been a lot more deforestation classified. And that's due to lots of reasons, like algorithms changing, more data becoming available, more sophisticated analysis, higher resolutions, these sorts of things. But when I updated it from 2021 to 2022, all the way to 2024, instead of this initial 3% increase from 2021 to 2022 data set, it's actually now 8.5% increase in the amount of deforestation in Indonesia. So if there's any analysis out there in the world that made an assumption that they were going to use the 2021 data set and now they update to 2022, it's probably going to have really significant changes if they're interested in deforestation. So if the data set changes, what about the published conclusions? And I had a published conclusion last year in PROPL, and I've updated it, but it wasn't necessarily very straightforward. On this page as well, I think is perhaps a useful conceptual model for how we might think about just 3 possible ways that our data is changing or is different. And I think that's size, privacy, and dynamism. And so here, I think is a good example with this data set in that it's very large. It's, I think, 10 meter or 30 meter resolution, but it's for most of the tropics. It's not being updated that often, internally maybe monthly, but kind of to the public every year. And it's very publicly available. But how do we then work in those different axes into like how we publish something? For example, how do we make a slide deck for PROPL? And I think the work that Rolly's doing is kind of related to that, but is not quite there yet in terms of authoring. Yeah. So moving on, the code is also another place where we should be thinking about, is the code repeatable, reproducible, and adhering to the idea that we can falsify hypotheses. I really like this quote from Baxter et al. On what is a research software engineer and what is kind of their job and what do they do. And kind of expanding the quote from what I've used previously, I was happy to see that they were also talking about the same principles within that work, like things being repeatable and meticulous. But the best part is probably that no one with the same casual attitude to experimental instrumentation as many researchers have the code would be allowed anywhere near a lab. And my own mistakes from last night kind of are perhaps relate to that. But I think it's a good thing to have in the back of our minds whenever we're thinking about how code can be used in the scientific method. It is not just, it's not something standalone, it should fit into that, and there's different ways that people build hardware or pieces of equipment like telescopes that have very accurate kind of data describing how they can be used and the precision they have, and yet we seem to just throw code about willy-nilly over the internet. And so I thought some questions might be useful. In what ways does writing code for scientific programming differ from conventional methods? And I think one of the main ones is that eventually there is usually some form of communication at the end. And we see that in things like literate programming. And that really does change the control flow of how we might execute a program. No longer are we writing a program and eventually we're going to run it as a standalone application. We're now discretely executing chunks of our program in an exploratory manner. And maybe we should be thinking about programming languages and tools that actually have that baked into them, unlike things like Python, anything inside a Jupyter notebook, where quite commonly people make mistakes where they change something later on that's actually doing some kind of mutation of data, and they run something from before, and suddenly they get different results. And then another question is, are the ways in which we publish and distribute software amenable to the kinds of things that we want for the scientific method? And I think the short answer here is that that's not true. I think we don't have the reproducibility that would be required for something to be considered a scientific method, and we can do a lot better. And I think we have tools that can get us a long way, like Docker, like Nix, and these things that offer some way of locking down all of our dependencies. But these are not necessarily extremely accessible to the programmer. And that is the last thing that I want to talk about, which is that the domain in which we're working in is not necessarily full of computer scientists. It's full of what Mary Shaw calls vernacular programmers. These are people that program by necessity, not kind of through choice, or they may choose to, but they're not necessarily coming with the same backgrounds as we might all think that our users will have. And so I think it's important to remember this whenever we are designing the tools that we're hopefully going to put into the scientific programming world. And in particular, I think we should be looking to have a tremendous amount of empathy for vernacular programmers, or people that don't know what necessarily a hash is, or don't know a Merkle tree, or these sorts of things. And so I think, as I said at the start of my talk, I'm really pleased to be following 2 other talks that I think actually do adhere to all these things. I think it's great to be seeing that. I'd like to just round off with some of our own work that hopefully is looking at doing all of these things in some way, which is building a kind of shell session manager that builds in reproducibility and the ability to undo your mistakes, which is at the moment called Shelter. The idea behind this tool is that it has tremendous empathy for the users, in that many scientific programmers are already having to use shell scripts and use a shell to do their work, but it is quite a unforgiving kind of environment to be doing your work, where there's lots of ways to do very destructive things without any way to recover from that. And the idea with this tool is that actually we can use all the things that we've been talking about already and provide a similar kind of environment where we're not asking people to learn too much more, but provide a lot more kind of low-level systems that are helping them. So for example, here, we're able to create 2 different distinct sessions, and later on, we're able to bring them all into the same place. Other things that are going on under the hood here is that all of the dependencies are being tracked for how files come into existence and the things that might be used in order to do that, and we're able to do that on kind of modern systems using things like eBPF. There's also the ability to merge different sessions, and so this can do the same analysis based on reading and writing to know that is it safe to do a merge, or actually should we replay what we've done because there's been changes in the dependencies. This is still very much work in progress, and I hope to keep the principles that I've been discussing kind of as part of the design of this going forward. So that's the end of my talk, and thank you very much for listening.
Thanks, Patrick. That was super interesting. I really love Shelter, although I want to hear more about that. But my question was actually about the kind of framing you had for the exploratory kind of programming, which I really liked as well. So you were talking there about kind of, you're often in this exploratory mode where you're not running the whole program to produce a kind of output. You're running a little fragment and seeing what happens. Have you also thought about that as a kind of end user affordance as well, like as a kind of comprehension tool? The world we live in now, it's very much, you have a static image or some kind of static output, and comprehension is, something that has to happen inside your head. It's not some kind of interactive relationship you have with the artifact. And I'm wondering if that same intuition you gave for programming could extend to kind of how I actually understand what I'm looking at. I might sort of tweak an input, see how the visualization changes, for example, and that's part of how I'm making sense of it.
Yeah, thanks, Rolly. Yeah, I definitely agree with that. I think that it all becomes, publishing things is stuck in the past a little bit. I think being able to provide end consumers of the information or the scientific things that we do with kind of the full artifact would be super useful. So one thing with Shelter in this particular example would be the ability to basically give them the entire or some portion of the entire execution environment for you to play around in. Likewise, if you can do that all the way through to the actual authoring tools that you're making, it would be great to be able to just do that in a web browser, for example, and not have to leave the comfort of the place where you're actually consuming the information. It gets really tricky depending on how big your data is, and as I was talking about before, those axes of what the data are, so the size, the privacy, and the other one that I've forgotten. Dynamism, right, which is maybe not as related in this instance, but if it does update, you would want to know that as well, so you can go back and check whatever you might add. Yeah.
Thanks for the talk. I'm wondering what your thoughts are about what the goals should be or what the end game should be. So we sometimes try to compare scientific programming to lab science. So you had that quote by Baxter, right? On the other hand, lab science is problematic in various ways and is constrained in various ways that software is not, right? Like you combine two chemicals and you can that can result in an explosion. You know, you can do all kinds of things in software without that kind of risk. So there's an opportunity for a lot more exploration. And we still have problems in the lab where you can't actually reproduce the experiment, right? Works in my lab, doesn't work in your lab. Why is that? So what are your thoughts about where we should be going? You know, 5, 10, 30 years in the future, what should we be trying to build?
Yeah, that's a great question. Thank you. I think one of the things that I find probably the most frustrating is that I don't think we need necessarily a lot more tooling. I think there is like a social aspect to this. That is that some of the things that make it hard to reproduce someone's results is just like, it's quite opaque. It's not, the code is just not available, or the methodologies that we write are so far removed from the code that we don't actually know, we can't reproduce it because it's not kind of precise enough. So I think trying to get more things like artifact evaluations into publishing conferences, both like ICFP does, but also in kind of more sciences that are using a lot of computation would be great. As for kind of more future plans, I think is similar to what I was saying to Ruli, which I think is kind of the ability for the actual ways that we publish kind of these results to be more kind of cognizant that it was made in a computational way, and having that actually part of the way that we author the end goal. So for example, here, presenting these slides, all of this is incredibly static, and I'm having to put in all the links to say, go and look at this source code, this thing was run on GE, and like you can come to me and I can give you that script, but there's no way for me to take the typesetting kind of languages that we have, whether it be LaTeX or types or something like that, and kind of have a really deep integration with also the data and all of the computation that went into it. So I think some kind of more unified framework for that would go a long way to helping this as well.
All right, let's thank our speaker again.